Onto IPv6. There are many reasons why you may start migrating to IPv6. Let's take a look and see what you will be dealing with when using IPv6 and what has changed. So just like before, here is the header. Let's focus on the important fields. So here are the IPv6 addresses. Here are the addresses equivalent to private addresses in IPv4, and this time the loopback address is only one, not a full range. The next header is similar to the protocol field, but it has changed. For example, fragmentation is now a new header that is appended to the IP header. So now there are additional headers that you can append to the main IP header. Here is the fragmentation header. Another big change here is that the source now fragments the packets. One thing that I didn't mention during IPv4 is that fragmentation is not good and should be avoided as much as possible. Big changes have occurred in this area. Let's take a look at them. Neighbor discovery. This is a replacement for ARP, which uses ICMPv6. It has other functionalities, but the main two are resolution of MAC addresses for routers and hosts. The solicitation might be a little confusing, so let me explain it inside Wireshark. So let me explain how the IPv6 solicitation actually works. We want a target MAC address, correct? And we have the target address. Here it is. It is F5D701, correct? Okay. The first thing that happens under layer 3 is that we send a message, a solicitation message, to a multicast group that is specifically made for solicitation, as you can see here, FF02, 1FF. And then the last 3 bytes of our target address, the F5, gets appended to the multicast group, so that when the multicast message is going to that multicast group, we know that the host is inside that multicast group. The next thing that occurs in layer 2 is that the same event occurs, but again in layer 2, we send a multicast message to a multicast group, as you can see, IPv6 MCAST FF. And then the last 3 bytes will be the destination target address's 3 bytes, just like the previous one, F5, right? And this is really like the more important part of the solicitation and the advertisement. If you understand that, the rest is quite simple, because then target address gives us the answer inside the ICMPv6 options. So it says that my link layer address is this. There are ways to automatically configure a network, but we will then lose all the functionality a DHCP server gives us and create chaos in the network. So a DHCP server is really mandatory. Here are the DHCP message types, and take a look at them. So with that, IPv6 is finished. Let's do a few demos. We're not covering IPsec, but I really want you guys to take some time and do research on it. If you have any application that you know that is not secure, or you want to make it even more secure, IPsec is a great way of doing that. Okay, so for the IPv6 demo, let's take a look at IPv6 fragmentation. It's a little bit different. As you can see, the first packet that you'll see is going to be your IPv6 packet. You will come with the next header of 44, which is the fragmentation header. That's the important part. Then you will see the fragment header. Inside it, we will have the next header. What is it going to be? Is it going to be TCP, UDP, ICMP? So here is UDP, right? We have reserved, we don't care. Then we have the fragmentation part, which is important for us, the offset. The first packet will obviously be 0, and then we will come with the more fragment bits, as in there are more packets coming, or more fragments that are coming after this, and we have an ID. The next packet comes in, same ID. Then here we have the offset. The offset will be the length minus the fragmentation header, as you can see here. then the same next header, UDP, and then it will suggest that, hey, this is 0, no more fragments are coming, and then we have the UDP and the DNS header. So this is how you would see IPv6 fragmentation inside Wireshark. Okay, now how would we see IPv6 using tcpdump? Well, if we take a look at the pcap file, normally, if we run it without any of the verbose commands, we will see frag, which it is an indication of fragmentation. Now, what is this? So what this tells you is that this fragment needs to start with the beginning of 0, the offset of 0, and it needs to move forward the offset of 1448. Again, it is the length minus the fragmentation header. Then the second fragment, which is the last one, as you remember, it is going to need to start from 1448 and it need to move an offset of 61. And here, the other information here is the UDP and DNS information. As you can see, it is not appended to the last fragment, interestingly enough, inside TCP. Now, what if we use the verbose command? Well, if you take a look, now, one tip, if you don't like things getting wrapped around, you can try this with the less and the capital S option. It makes it far easier to understand what's happening. So you'll see the fields like the flow label, hop limit, the next header, pretty useful, and then the payload length. If you go further down, you will see the ID, which we didn't see previously, and you will see the field that I just explained, the offset and how much it needs to go forward. And again, you will see the UDP and DNS information in the first one appended to the ending of the first fragment, interestingly enough. So this is how you would see IPv6 inside tcpdump. The transport layer. Let's start with TCP. TCP is reliable, which means that it detects errors and retransmits the packets, and is connection oriented using the three-way handshake and then sends data. Here is the TCP header. TCP ports range from 1 through 65,535. Anything below 1023, well, 1023 included, is called a privileged or a known port, and anything above that, 1024 above, is called ephemeral port. When a connection occurs, a TCP connection, each device will choose a random sequence number, and for each byte that it sends, the sequence number gets added. There is an exception here though. The fin and the SYN flags in TCP are counted as one. The main purpose of the sequence number is for the reliability of the TCP protocol, and it uses those to figure out whether packets have reached the destination or not, and should it retransmit again. So it kind of acts like a key to a connection as well. Now, the acknowledgement number is pretty much the same sequence number that each device will keep the other device's sequence number in their acknowledgement number. Essentially, they are acknowledging that the sequence number that the other device is telling them, they're like, okay, you gave me the sequence number, I acknowledge that, and I know about it. The header length, to get the correct amount, it has to be multiplied by 4. Now, the header without options is 20 bytes, but in TCP, seeing options, it is quite common, and it's not like IP. So seeing this be more than 20 bytes is very common. So before we continue with the fields, let's talk about the three-way handshake and how it works. To initiate a connection, the client will send a packet with the SYN flag set. The server will send back another packet to the client. This packet will have the acknowledgement number, which will be the client's sequence number changed to the correct amount. Now here, because only the SYN flag exists, it will only be added by 1. The sequence number will be its own, and in the flags, the SYN and the ACK flag will be set. Then the client will send back another packet, which in this packet, the sequence number will be the changed acknowledgement number of the previous packet. The acknowledgement number will be the sequence number of the server packet changed again because only the SYN flag existed. It will be only added by one, and in the flags, only the ACK flag will be set. So during the IP, we mentioned ECN, but we said that we will cover it during the TCP section. Let's find out how ECN flags work during the three-way handshake. First thing to remember though, the two first bits are in the IP layer and the last two bits are in the TCP layer. So during the SYN, we will have zeros in the IP and fully ones in the TCP layer, which is called an ECN setup SYN packet. Then the SYN-ACK will come from the server having three zeros and one at the very right side in the TCP section, which is a ECN setup SYN-ACK packet. Then the client and the server will send 0 1s or 1 0s, as you can see, which indicates that no congestion is happening and everything is fine. Now, if congestion occurs, the IP part will be 1 1 and the TCP part will first be 0 1, which means that we are echoing the congestion, and as the acknowledgement part, we will get 1 1 1 1. Now, normally ECN doesn't matter, but why do we need to know these? Well, when creating filters or looking for indications of compromise, how different events are affecting our packets is important, because we might miss or create false positives because we didn't take into account these types of changes. So it's important to understand how different events are changing the packets. The only thing that I want to mention about these is that be aware of them and take a look at them for either any type of adversary activity or any sort of evasion tactics. This field allows each device to tell the other end how much data they can receive, and it acts as a buffer, and it can change. So you could say that it works as an offset for the sequence number, as in how much further you can go into it. If this field reaches 0, it means that the end device can't handle any more incoming data and it should get investigated. We say that a packet with an incorrect checksum should get discarded and retransmitted, but this can easily not be the case, and you may have packets going back and forth with incorrect checksums simply because no one is checking for them. Well, when I say no one, none of the devices are checking for them, so this could easily be the case. So just be aware of that. And TCP has options. The maximum segment size is for reducing fragmentation as much as possible. The timestamp is for discarding old packets that have been wandering your network. And the no op is for padding the options field to a multiplication of 4. With that, let's do some TCP demos. Okay, so let's do some TCP demos. Let's first start with the three-way handshake. Let me actually show you how it works both in Wireshark and TCP dump. So let's start with Wireshark. As you can see, as we previously said during the slides, the first packet will send a SYN packet. Now, as you can see, now here is the relative number. Wireshark and TCP dump will make it easier for you, but this is the raw number. You can look at the last like two numbers, and generally that's going to be enough. For example, here's 24, right? Acknowledgement number, we haven't gotten anything. We send the SYN flag, and other things don't matter as much. Right now, what do we get next? From the server, we get a SYN ACK. As you can see, what do we get in the sequence numbers? The sequence number, the acknowledgement number. Let's first do that. It's 25 now. Why? It was 24, as you can see, because of the SYN, it gets added by 1, now turns to 25. Now the server has chosen a random sequence number for itself. Now, this sequence number will now go inside the client's acknowledgement number. Now, because here we only have the SYN flag, it will get added by 1. So again, the ACK comes from the server. The acknowledgement number has went from 40 to 41, and the sequence number obviously stays the same from the previous one, as you can see. And the last flag is going to be an ACK flag. So that's the three-way handshake. Okay, let's take a look at the three-way handshake using tcpdump. Now, normally if you don't run any type of options, as you can see, you will see the flags the same. You will have the sequence number, the window, and the options. And again, at the SYN-ACK packet, now, interesting thing here for maybe some of you is that the ACK is used as a dot, not an A. Some of you might get disappointed by that. Then you will have the sequence number and the acknowledgement number. In the first one, you will not have the acknowledgement number, nor you'll have the sequence number in the third one. Now, in the third one is a little bit confusing for you because it is 1, right? So it's showing the relative number. If you want to get the absolute numbers and not get confused, because here it's like it's the absolute number, then it's relative, you can use the capital S. And with the capital S, it is a little bit easier, I would say, to use the absolute numbers because then everything is consistent and you can see that, okay, the sequence number, then the sequence number, here is a new one that is chosen by the server, and here it is added by 1, and again, the acknowledgement number of the client or the sequence number of the server here has increased by 1. So everything is working pretty well. Now, this is the normal version, right? What about verbose? Well, I would say sadly or happily, the normal version is actually enough because with the verbose command, you will get IP information, which you may or may not care about, and you will just get the checksum. In the other parts of the information, nothing, as you can see, changes. You get the same sequence number, same acknowledgement number, same window, and the same type of options. So the verbose command isn't, I would say, useful when it comes to TCP. So that's that with the three-way handshake. Okay, let's do another TCP demo. I will first show you a retransmission, then I will show you two different type of scans, right? So as you can see, here is a push ACK retransmission, and the retransmission in the flags, it won't matter that much, but if you take a look inside the TCP, in a retransmission, the same packet will get sent to the very same port, and all the information, the checksum, as you can see, the sequence numbers, they all will be the same. Now, if you take a look at the timestamp, though, as you can see, it will start at 0 and then gradually increase to like 1 and 2 seconds, 4 seconds, and so on and so forth. So the timestamp gets increased the further down it goes. Now, if I show you a SYN scan first, not the TCP scan. So let's surf, okay, the SYN scan, yeah. In a SYN scan, what happens is that, well, the scans will happen to different destination ports. So as you can see, the destination ports change. The checksums change. If you take a look back again on the retransmission, the checksum doesn't change either. Here it is, as you can see, the checksum doesn't change. But it does in a SYN scan. And the timestamp, if you take a look again, they will all be 0 because each packet is a new packet. It's not, you know, from the beginning of that. It's essentially a new packet that is coming, all with the timestamp of 0. So things that change are destination ports and the checksum. So these are two ways that you can check and timestamp check if a SYN scan is happening. Now, if you take a look at, and also you will get like a lot of resets, maybe you may not get these, you may like block these and so on and so forth. But now if you take a look at a TCP connect scan, right, which is similar but has some differences, let's take a look again. If you take a look first, well, destination port obviously changes. If you take a look, the sequence number changes as well, and the checksum changes as well, and the timestamp will still be 0. So the difference between a SYN scan and a connect scan is that the sequence number changes. A retransmission, which is normal activity, It goes to the very same port, the checksum stays the same, the sequence number changes, stays the same. The only thing that changes and increases is the timestamp. So this is how you would see scans and a normal retransmission. Advanced TCP dump filters. TCP dump uses BPF filters to select any packet inside a PCAP file. Now, previously we talked about the macros. These are easier ways or easier filters that are essentially pre-made and you can use. But then we have the manual ones like IP 0, TCP 13, and so on and so forth. Now, what does that number actually mean? That is the byte, and if you refer back to the headers, when we want to check to see if a field, like what is the byte offset of that field, you start from the very top, you start with 0, and each row that you go to the end is 4 bytes. So essentially it's 0, 1, 2, 3, the next row, and then 4 all the way to the next row, and then starts with 8. So you could making it a little bit easier, if you take a look at the headers, from the left side, the first row is 0, the next one is 4, and the next one after that is 8, and again this just continues on and on. Two things to mention here. A is that you can give decimal values, and B, if you refer back to the TCP header and take a look at the TCP filter here, as you can see, it starts at byte 2 and it has an offset of 2 bytes. Now, remember, the offset starts from the beginning of the location that we are, not at the end. So the 2-byte offset is the whole destination port. It doesn't go beyond that. Now, normally you can only check 1 or more bytes, but if you only need half a byte or a single bit, what would we do? Well, for that we use AND. If we care about a bit, we will AND it with 1, and if that is not the case, then with 0. So here is a bit example. If ECN exists and we don't care for either the URG flag or the ACK flag, we can AND it with just O2. But if we don't want to see the urgent and the ACK flag either, we would AND it with 3.2. So here are a few more examples to get you going. As you can see, you can write different filters, and these filters can get combined together with ands and ors as well. So you don't need to just write one filter. Okay, so T-Shark, we are not covering it, but I have one slide for you. Can T-Shark replace TCP dump? No, it can deal with larger PCAP files, but not like TCP dump. Is it useful? Yes, it is extremely useful, especially for layer 5 and applications. Here are a few examples to get you started with T-Shark. Previously, people would say if you want increased speed or if you want to stream a video, use UDP. Nowadays, with the increased speed, pretty much everything uses TCP. The issue is that some protocols are still using UDP, like DNS and DHCP. Now, because there isn't much to cover here, I will only be going to be showing the header, and that's pretty much it. Here is the header.